Hey guys, thought I'll just do sort of like a video just to show you like a sort of like a full walkthrough for this kind of problem because the one thing I just want to be really sure is that sort of like everyone knows how to do everything, and some of you may be a bit patchy with your background mathematics knowledge. So this is kind of a walkthrough, like a full walkthrough, sort of catering to the sort of like the lowest common denominator in terms of knowledge. Not that I mean it as an insult, but I just really want to make sure that like everyone knows what needs to be done with this kind of question. So as we've addressed before in the tutorial, or for those who are just stumbling through this to this video randomly, here's the linear programming problem where we can just simply formulate a linear program and solve it via a graphical method. So it's fairly straightforward. So to feed the stock, the farmer can purchase two types of feed. He has decided each day his herd requires 60, 84, and 72 some nutritional elements A, B, and C respectively. The contents and costs of a pound of each of the two feed are given in the following table, and you can kind of see the table just detailing pretty much all the information you need. And basically at the bottom, formulate a linear programming model to minimize the total cost of feed and use the graphical method to solve the LP. And just the second question we'll just ignore for this video for now. So the first thing, it's very easy to get caught up in this kind of problem, mainly because there's just a lot of text, there's a lot of information, and a lot of people without experience won't know where to start. So the first thing I usually do is that I try to so what I'm just gonna do, I'm just gonna switch it to so that you can sort of just see me write down my thoughts and just sort of see how I do things. So what I do is that basically I look for common oh dear, it looks like my camera's just sort of shifting in and out of focus. I'll just quickly figure that out. Camera control. Let's turn off the focus. Apply. Okay, thank you. Let's hope this works. Alright. Right, so usually with these kind of problems, and just to refresh your memory, a linear program has an objective function and constraints. And usually like the objective function and each of the constraints will sort of just refer to like an individual resource or topic that is mentioned in the problem. So like say one way you can think about it is that you can sort of think it, or you can rewrite the information in such a way that possible topics. So just do topics, and then you could think, well, you think there's gonna be like part A, part B, part C, and then there's also the cost to think about. So in a way you could sort of just see, okay, well there's V1 and V2 as well, and as you can imagine by now, you can sort of just think, okay, well why don't I assign V1? I should probably do that the other way, as x1, as our variable x1, and we'll do V2 as our y. For some problems, it's not very straightforward to figure out what kind of variables you might need to see, so this might be something you just have to experiment, and then until you find something that works. It can be frustrating, yes, I'm aware, but that's kind of just how it is, and sometimes the problem in itself can be confusing. So the next thing I see is that I'm thinking in terms of topics. I'm looking at the A, and then I'm looking at the problem description and just seeing, okay, A, well, the one thing we could do, actually, I'll just cancel that one there. The one thing you can also do is sort of rearrange the information that is actually is in a different table that allows you to sort of write out the linear program. So what you can also do is sort of like V1, and then you could do V2, and then just remove the corresponding variables X and corresponds to variables Y. And then I'm thinking, okay, A, and then well, it's kind of, you could just see sort of in the table on the right, to see if I could do it in the camera properly, that you sort of just flipping the table around. So you can sort of just see that it fairly easily follows 3x plus, and then just copying the coefficients from the table to y, and then from the main text in the question, it's just right up the top, so it should be 60. So the other thing is that each herd, in the second sentence, it says he has decided each day his herd requires 60, 84, and 72 units of nutritional elements. That means we don't want any less of it. But it doesn't matter if it actually goes more, because then it's already satisfying the requirement. So we can simply go with a greater than or equals constraint, so that the 60 goes there. So I'll just cancel out this topics, and then the other constraints follow fairly easily. So you can sort of just see 7x plus 2y, again going down the second column of the table. well, sort of going down the B column, and then in the same way, we can just continue. So that will be 84, and then similar for C. So the point I want to stress is that what we're doing right now in terms of the constraints is that we're grouping all the information pertaining to nutritional element C together. And that's basically the strategy I try to use when I'm formulating these linear programming problems. And that should hopefully make the situations or further problems easier to process for some of you. So moving on, just finish that last one. 6y is greater than or equal to 72. Alright, now the objective, which is actually to minimize the cost. So I'll just click objective. And then it's to minimize the cost. So that's our objective function. Now, of course, going along with my previous, what I said before about sort of just finding the information that's only relevant, you can see in the final column on the right is that with the costs, there's already another 2 columns there with the 10 and 3. So in the same way that we have the constraints, we can also attribute, or we can also figure out our objective function for the cost to just simply be 10x plus 3y. So, and basically we want to minimize this. So I'll minimize. I don't even know how to spell minimize. Excuse me. I-M-I-Z-E. Thank you very much. So basically we just want to minimize this function with respect to the following constraints. And okay, so now that we've got our linear program, it goes to show that we've got to figure out how to solve it. Alright, so let's just see. Well, I'll take this sheet off and I'll just rewrite the whole LP in actual proper order, so that, and then I would still draw the graph so that you can guys see everything that you need to see. So the objective function, that's z equals 10x plus 3y. Alright, that looks good enough on the camera. Alright, so, and then constraints such that, and then constraint A, so that 3x plus 2y is greater than or equal to 60. 7x plus 2y is greater than or equal to 84, and 3x plus 6y is greater than or equal to 72. So basically what's happened now is that we can start sketching the graph and sort of get an idea of what our feasible region would be. And some of you had a bit of trouble doing that, since it might have been a while since you drew a linear graph. So Basically, since each of these equations are inequalities, you can basically sketch them on the graph as sort of like with a straight line, and then you can shade in a particular area. So the question is, how do we do that? So I think the easiest way to look at it is that if we just take a big axis first. So I'll draw a big axis at the bottom. But what I do, and what is probably the easiest way to do this, just do x and y. Is that I look at these, I pretend they're equality constraints, and the easiest way to find the two, basically to draw a line, you only need 2 points on the same line. So here, the easiest way to do it is to have, what's the best way to present this? So I think I'll just go through the method first. So first, assume, let x equals 0, and then y is equal to what? So x equals 0, y equals 30. And so that's a point on basically the that's a point on the y-axis where our first point is. And then the second point will be, if we let y equals 0, then it means that x is equal to 20. I'm going to assume that you're capable of following the basic calculation, which is, so it's like x equals 0, then y is equal to 60 divided by 2 equals to 30. So we'll do that for the rest, and so that we can get a better idea of our axis. So x equals 0, y equals 84 divided by 7, which is 60, 72, 84, 12. And then y equals 0, so I'll put the 0 there first. I cannot think, so x equals 0, y is equal to 42. And then y equals 0, x equals 12. That's better. Alright, and then the final one, let's see, x equals 0, y equals 72 divided by 6, which is 12. And then y equals 0, put the 0 here. And then x is 72 divided by 3, which is 24. And then so that gives us a pretty good idea of how large our axes are. So we can just probably do it in increments of 10. 10, 20, 30. Again, you only need to do a sketch. So it doesn't need to be like so neat, so perfect. It's just meant to sort of just give you an idea of what you expect to see, and then we could just plot each of them. So, let's see, 0 to 30. So 0 to 30. That's, you know what? Let me try and okay, we'll do. So that's 10, 20, 30, 10, 20, 30 to give you guys a bit of perspective. 10, 30, and then 20, 0, and then we could, you know what, I'm gonna be lazy, I'm just gonna pretend that I'm competent at drawing lines, so we'll do just that, and then just to refresh your memory, this is A, this is B, this is C, and we will label our constraints as follows. So this is A, and we'll actually find a different kind of pen. Alright, so B, okay, 0, 42, so 0, 40, okay, that's a bit further up. I did not anticipate that coming. Well, I probably could have, but moving on in the same way, we plot the two coordinates and then we can draw a straight line between them. So again, with my marvelous freehand skills, I'm going to draw our constraint B, and then lucky last but not least, we've got constraint C, which is 0, 0, 12, which is about here, and then 24, 0, which is about here. So that would give us we just freehand draw this line, and then we have C. Now, the other thing to keep in mind is that the other thing to be careful about is that also the type of inequalities that you're dealing with. So this is greater than or equal to. So if you look at it in terms of, let's do it with A first. So you can imagine A has all its inequalities where x and y is greater than or equal to 84. So it's basically this whole shaded area, including the line itself. So I think, just trying to think of a way that's least messy, but perhaps it's easier. Well, I'll just do this first. So there's just kind of shade this area. Alrighty, and then we would do B. So B again is the greater than or equals to. So but it's greater than this line. So that's kind of like this area. And then we've got, for lucky last, our C, again, it's another greater than, so it's sort of like all this area up above the blue line. So let's see which direction selection. So now we've got quite a mess, in which now I would sort of switch over to this little applet that I showed during the tutorial. So you can see how it's sort of just very similar to what I've just drawn. And I think, but the most important thing I want to highlight is the feasible region. So the feasible region, as you probably learned already, is sort of the range of points in which you can have your x, you can have your x and y such that they still satisfy all the constraints. And if you can probably see in the GeoGebra diagram already, so I'll just indicate with the pointer that you can see sort of like this brownish area. That is the overlap of all possible feasible regions. And then it's like here on this graph, I'll just try and sort of just make a really, really thick line that indicates sort of like the border, the barrier. So you can sort of see what I've drawn here pretty much resembles what I've sort of drawn on this GeoGebra applet. And in the same way, I've got this line here with actually a few key points, which I'll actually just sort of mark with a very big black spot. We've got these same points like here, this one up there, and then this one here, which is about down here, and then we've got this one, which is about here, and then we've got this one, which is down there on the x-axis. So just for a bit of clarity, I'll move that pen off the paper. So just for a bit of clarity, if you sort of look at the GeoGebra app, I'll put a link in the description below as well, so you can play around with the app on your own. Now, the final thing to do is to sort of say, okay, now I want to find the values that minimize my objective function. And so when you do it by hand, sort of one of the ways you can do it is that you can rearrange the objective function into some x like y equals x something. So it's probably, and the one way you can think of it is that it's basically your constant. So let's see if I could rewrite the objective function to 3y equals z. minus 10x, and then I'm just going to divide that by 3. So y equals z over 3 minus 10 over 3x. And so since we've got a negative gradient, you can imagine the slope will be negative in some way. So you're probably thinking of a line something like that. So I will save the trouble of drawing on my graph and go straight to the GeoGebra app on the right, where you can see that I've sort of just already drawn the thick back line. So, but the thing what I'm doing now is that I'm changing the values of z such that my line will sort of just keep moving left and right as I drag across the slider. Again, you can do this within the app yourself just to sort of just figure out how things work. Now, again, this is where we've got to remember the sort of like the main goal of the question. We want to find the value of z that we want to find x and y such that z, the number z, is minimized. So since we want to minimize z, it makes sense that we bring our objective function in from the right until we find a point where this line coincides with some point in the feasible region such that z is as small as we can possibly get. So I don't quite remember the right number for this problem. I think it was z equals 123. I can't quite reach it, but you sort of get the idea. Another thing in general too that you can sort of just take from this is that in certain situations you can sort of look at extreme points where when I say extreme points, it's sort of like these points I marked earlier. So these ones. Look on the left, because essentially they are the intersections of the constraints at like sort of like the extreme area, and those are most likely, not necessarily in all scenarios, but they will most likely be the first few places you want to look. But for other situations, it's probably easier to have your objective function line, and then just sort of just use it to give yourself a visual idea of how or where to start looking. And so but since we can easily just look at the extreme points, and then we just go to the diagram on the right, and then we just use our line, we're probably just thinking, okay, well, it looks pretty close to this point. And now this point is the intersection of which constraints? It's B and A. So what we're going to do now, just go to the next sheet. So I'm just going to rewrite B again. So B is constraint 7x plus 2y greater than or equal to 84. And A is, silly me, 3x plus 2y is greater than or equal to 60. Now, of course, if you don't remember how to find the intersection coordinates, we can simply just solve these as a series of simultaneous equations. So I'm just going to go B minus A. And if you can sort of, you know what, I'll just write it out just to make sure that you can really see it and don't have to do so much in your head. 2y, I'll just make that equal 60. That's probably a bit easier. Doesn't really make much of a difference anyway. Plus 2y equals 84, and that's B, that's A. So don't remember how to do simultaneous equations? This is where it is for you. So that becomes 4x equals 60 minus 84 is... I'm feeling that something is a bit wrong. Yeah, I thought something was right. That's 84, and that's 60. My apologies. So that's 4x is equal to 24, which gives us x equals 6. Substitute that back into A. So sub in A, and that gives us, let's see, 6 3s are 18. 18 plus 2y equals 60, and that gives us 2y equals 42, y equals 21. And there we have it. So we have our coordinates xy equals 6, 21, which minimizes our objective function with a... Well, basically what you can do now is that you can substitute this into the objective function. So to refresh your memory, the objective function was 10x plus 3y. So now that, and then it's equal to z. Now that we have our xy that minimizes this objective function, we can have, so we can substitute 6 and 21 in. So that gives us 60x. Well, no, just 60 plus 3 times 21. That gives us 60 plus 63 equals 123. And you can sort of verify that on this graph, where you can sort of just see I've got z equals, can't quite get 123 but 124, but at the same time you can see it coincides with this point, which is the intersection of inequality A and inequality B, which is the green one. I'll just move that out of the way. Now you can see it's almost fairly close to up here, but not quite. Again, I will leave it as an exercise for you to test the value here and see what z value you get, and ultimately just see which one gives you a smaller z value. So yeah, hopefully this is helpful. Do let me know if you have any questions or you don't understand any part of the process, but hopefully this is sort of made a bit easier for you despite my various mistakes. So thank you for watching.